the position vector rt and the momentum vector p. Any other physical quantity relevant to the system can be calculated in terms of these two dynamical variables r and p. If we want to measure the values of these variables at any time t prime, we can predict using, for instance, Hamilton's equation dx by dt is equal to del x by del p and dp by dt is equal to minus del x by del x. The quantum mechanical counterparts to these ideas are specified by postulates which enable us to understand how a quantum state is described mathematically at a given time t, how to calculate the various physical quantities from this quantum state, and also knowing the system's state at a time t, how to find the state at any letter t prime, that is, how to describe the time evolution of a system. All these are known with the help of these postulates. So let's study about these five postulates of quantum mechanics. The postulate number one is the state of a system. The state of any physical system is specified at each time t by a state vector ket psi in a Hilbert space H. The ket psi contains and serves to extract all the needed information about the system. Any superposition of the state vector is also a state vector. The postulate number two, that is the observables and operators. So, friend, to every physically measurable quantity, if you want to measure any physical quantity A, so for each this measurable quantity A to be called an observable or dynamical variable, there corresponds a linear Hermitian operator A. So that means for every measurable physical quantity, there corresponds a Hermitian operator A whose eigenvectors form a complete basis. Now, postulate number three, measurements and eigenvalues of operators. The measurement of an observable A may be represented formally by the action of operator A on a state vector ket psi. The only possible result of such a measurement is given by one of the eigenvalues an of the operator A. If the result of the measurement of A on a state vector ket psi is an, then the state of the system immediately after the measurement will be different and is given by a projection of ket psi onto the eigenvector ket psi n corresponding to eigenvalue an. Therefore, ket psi after the measurement can be written as, so we see that if the measurement of an observable A is made Then, after measurement, the state vector changes. Now, postulate number 4, probabilistic outcome of measurements. In terms of discrete spectra, when measuring an observable A of a system in a state vector ket psi, the probability of obtaining one of the non-degenerate eigenvalues an of the corresponding operator A is given by Pn an is equal to norms square divided by bracket psi, where psi n is the eigenstate of operator A with eigenvalues an. So this is the probability for non-degenerate eigenvalues. If the eigenvalue an is m degenerate, then Pn, the probability of obtaining the one of the m degenerate eigenvalues can be given by Pn an is equal to summation j is equal to 1 to m modulus bra psi n j ket psi square divided by bracket psi. The act of measurement changes the state of the system from ket psi to psi n. That means if we operate an operator A on ket psi, then it changes to ket psi n with eigenvalues an. If the system is already in eigenstate ket psi n of an operator a measurement of A yields with certainty the corresponding eigenvalues an. That is, in that case, if the system is already in an eigenstate psi n, then after operating the operator A on ket psi n will certainly yields an eigenvalue an. Now, the in terms of continuous spectra, the probability of obtaining one of the non-degenerate eigenvalues can be extended to find the probability density that a measurement of operator A yields a value between A and A plus dA on a system which is initially in state ket psi, then dp by dA is equal to psi a norms square by bracket psi is equal to psi a norms square divided by integration minus infinity to infinity. For example, the probability density for finding a particle between x and x plus dx is given by dp by dx is equal to psi x square by. Now we'll learn about the postulate number 5, time evolution of the system. The time evolution of the system, the time evolution of the state vector k psi t of a system is governed by the time dependent Schrödinger equation. I s cross del psi t by del t is equal to Hamiltonian operator k psi t, where h is the Hamiltonian operator. So these five postulates fall into two categories. The first four describes the system at a given time, and fifth shows how this description evolves in time.